All right, let's look at the vocabulary word acceleration. We recently viewed a graph that looks like this, and this was a velocity time graph. So if I look on the y-axis, I see the y-axis is labeled velocity. The x-axis is labeled time. So when we are looking at a velocity time graph, the slope is now going to be something other than velocity. Velocity is already my label for the y-axis. So if I am looking at this graph and I want to calculate the slope, that's going to give me information about how my y-axis is changing as time goes on, okay? So if you are sitting in math class, you will calculate your slope by using rise over run, or you might be used to saying y2 minus y1 over x2 minus x1. So that is our format for calculating slope in general from a graph. If we were to calculate the slope value for segment BC, I'm going to say my y2. So BC, here is the second point on that line. So y2 has a value of 5 minus y1. Point B represents y1, and that has a y value of 0. So I have 5 minus 0. My time is going to be 2 minus 1. Please be careful. At point C, we do have a value of 2 seconds, but this segment did not start at 0 seconds. Point B started at the 1 second mark, okay? So always pay attention to the details. So the slope value for segment BC is going to be 5. If I were to calculate my slope value for segment DE, now y2 would have a value of 0. y1 would have a value of 5. So 0 minus 5 for my numerator on this part of the graph. Then for my denominator, my time ended at 4 seconds, but it started at the 3 second mark. So my slope value for segment DE is going to be 5 over 1, which gives me, negative 5 over 1, which gives me a negative 5. So these two slopes both have a value of 1, but segment BC has a positive slope value, and segment DE had a negative slope value. Hopefully this is something that you are already comfortable with from your experience in math class. So the next question here on the page says, what are the units for this slope? It's not meters per second, because meters per second is already my label here on the y-axis for my velocity. So if I look at these variables that I've plugged into my equation, and let me see if I can give myself a little bit more room to write here. If I look at the variables that I've plugged into my equation, I have my y-axis, which is measured in meters per second, and I have my x-axis, which I apologize, I did not put the label on this one. We've looked at it so many times. I got lazy. My x-axis has a unit of seconds. So my units would be meters per second per second. Most people would just simplify that to meters per second squared. All right, and it would be the same for both of my slopes. Meters per second, or meters per second squared. So what variable do we measure in meters per second squared? Well, this is our new variable today. Our new variable, meters per second squared, is the unit for our acceleration. And so you can see that I have written out for you what the word acceleration means. It is the change in velocity that takes place, which was our numerator, divided by the change in our time, or just simply how much time did it take for that change to occur. So our acceleration is defined as that. The rate of change in velocity or the change in velocity over time. Acceleration, I like to describe is how quickly this change happens. So it says here using displacement in time. We're going to trade that out, and we're going to have that say using velocity in time. Using velocity in time. So how quickly does that change in velocity take place? That is my acceleration. If we think of the cartoon movie Cars, Mater and Lightning McQueen are best buds, but they will not experience a change in velocity at the same rate. Lightning's going to experience his change in less time than Mater. So Lightning would have a greater acceleration rate. He conducts that change, but in less time, okay? Acceleration is a vector quantity. So it is going to be able to be illustrated using arrows. It has magnitude and direction. That's what it means to be a vector. And as I stated before, the units are meters per second squared. So here is our explanation of acceleration's equation in words. But this is the formula that I want you to be most comfortable with. When we introduced slope in a previous lesson, we introduced that symbol delta, and we said delta means change. So here's my delta. And then I asked you to write for yourself that change in anything is going to be final minus initial. So when you look at my equation, this is V final minus V initial. What is our final velocity? What is our initial velocity? We are subtracting them, but in this specific order. So if we go back and look at this graph once again, the slope on this graph represents acceleration. The slope on this graph represents acceleration. We are going to describe now our velocity, because remember, acceleration is the change in velocity. So this question states, does the velocity change during these different segments? So does the velocity change during segment BC? Well, the velocity was 0 and now it is 5. Yes, the velocity changed in segment BC. How did the velocity change? In this case, it was an increase in velocity. Or maybe you were more comfortable saying that the object sped up during that segment. But that is an acceleration because there was a change. In this case, it was an increase in speed. And so that is what our acceleration rate will tell us, okay? Then we are going to look and see for segment CD. Does the velocity change? Right here, does the velocity change? Well, at point C, it's a value of 5. At point D, we're still at a value of 5. So for this segment, no, the velocity did not change. So what we would say here is that velocity is constant. And if we wanted, we could give the specific value of 5 meters per second. Then I'm going to add another one that's not on the screen. Let's look at segment DE. Here, is my velocity changing? Yes. My velocity was initially a 5. Now we are down to 0. So my velocity did change. How did the velocity change? Well, in this case, we experienced a decrease in velocity. We started at 5, We ended at 0. So you might also choose to say that my object slowed down. All right. Once again, having an acceleration value here is going to tell me that my object changed velocity, and it's also going to specifically indicate that my object slowed down. The next question here is, what is the significance of a positive and negative slope? Well, slope represents acceleration. So when I look at my first segment, BC, this was a positive slope or a positive acceleration. My object is moving in the positive or forward direction, so this object sped up. If I look at segment DE, this is a negative slope in math class, so this would be a negative acceleration. Once again, my object is moving in the forward or positive direction, so a negative acceleration means that my object slowed down. There was a decrease in velocity, okay? Now, I skipped over segment CD, so let's just address that very briefly. If we were to calculate our acceleration here, we would get a value of 0. Whenever my velocity is constant, we would say that there is no acceleration. Acceleration is 0, no slope, okay? If we were to calculate the acceleration of these different segments, we could use the acceleration equation where it tells me that I'm going to say final velocity minus initial velocity divided by time, or I could use my slope equation, y2 minus y1 over x2 minus x1. What we're going to find is that it gives us exactly the same data and exactly the same final answer. So we will quickly do BC. I'm going to calculate my slope or my acceleration. They are the one and the same on this graph. So I am going to say 5 minus 0 over 2 minus 1 for a value of 5 meters per second squared. Now I'm going to calculate segment DE. My slope is my acceleration. So in this case, I'm going to say 0, because my final velocity was 0, minus 5 over 4 minus 3, which gives me a value of negative 5 meters per second squared. Okay, so when I calculate my slope value, what I see is that my acceleration is a positive number when my object is increasing velocity, or when I have a positive slope on my graph. My acceleration was a negative number when my object is decreasing velocity, or I have a negative slope on the graph. Again, I am focusing right now on an object that is currently moving in the positive or forward direction. If I were to tell a story for what is happening on this slide, I would say that I have a student who is in the parking lot. They are in their parking space trying to leave after school. At the beginning of the story, they are sitting parked in their car. They are going to attempt to leave their parking space by slowly pressing on the gas pedal. So they've reached a speed of 5 miles per hour. We'll say it's miles per hour. They feel like it is clear for them to exit their parking space. So they are going to stay at 5 miles per hour, but only for a second, because they see that there is a car coming. And so although they are still in drive, they are still moving forward, they have decided that they should take their foot off the gas pedal. And perhaps they are applying the brake now so that they come to a stop. They have decided while they are stopped that that car is not slowing down, and if they stay where they are, they will get hit by the other car. So the driver now decides to put their car in reverse and step on the gas pedal as they back up and return to their parking space. We did not talk much about the bottom half of this graph, so let's do that really quickly. For segment FG, I want you to know that the object in segment FG is speeding up because my object starts at a value of 0 meters per second and increases to a value of 5 meters per second. They are simply moving in the negative, reverse, backwards direction. Okay? We have not talked much about our displacement over the last couple of lessons, so let's go back and revisit that variable displacement. Remember, displacement tells us how far, and it does specifically have a direction. Remember, it's from point A to point Z, how far from there. So if we are looking at a velocity time graph, and I ask you for the displacement of the object. So in real life, how far did the object travel before it came to a stop? If we are accelerating at this rate and the object needs to reach 50 meters, how much time will it take them to reach that 50 meters? Real life scenario, you are driving your car at some speed. A child runs out into the street. You are braking with an acceleration rate of blah, blah, blah. How far do you travel before you come to a stop? Real life, would you hit the child in the street or would you stop before you get to them? Okay, so these are the things that we would be asking you for, where you would need to relate displacement to our velocity, our acceleration, and our time. If we're looking at a graph, we are going to find our displacement by calculating the area of the slope. The area under the slope. So if we are trying to calculate for segment BC, this area under the slope, you see, makes a right triangle. So if we are finding the area of a triangle in math class, this would be 1/2 base times height. In our class, later we will get some equations and we will see that this would equate to 1/2 of time times change in velocity, because that's what our y and our x-axis represent. If we were trying to find the displacement that the object experiences during segment CD, well, now this makes a rectangle. So to find the displacement here, we would say displacement is just base times height, okay? Which would just be velocity times time. Now, again, this is also in real application. Our formulas are going to account for the fact that my object is accelerating. So we will give you the full formula in the next lesson. But that is essentially how we would calculate our displacement, and just kind of a little description as to what variables are being tied together there.